All right, thanks for joining me. And today we are going to be talking about how to predict the products from those types of reactions that we talked about in the last video. So we learned about how the different types of reactions can be identified. And so now today we're going to talk about how to predict the products of those chemical reactions. So the first thing you have to do in order to predict the products is you have to identify the type of reaction based off just the reactants, because we don't know what the products are. So we have to look at just the reactants in order to figure out what type of reaction it is. So to do that, we look at the synthesis reaction. Remember, synthesis reaction is going to have two elements as our reactants, two elements, and those two elements are going to combine to form a compound. With a decomposition reaction, you're going to have only one reactant. So it's usually going to be just one compound. Well, it has to be one compound because elements can't decompose. So you're going to have one compound and that's it. Single replacement is always going to be an element and a compound, an element plus a compound. That's how you identify it as a single replacement. And then you're going to have a double replacement reaction, which is going to be an element, or sorry, a compound plus a compound. So you'll have two compounds. Now, the exception to the single replacement element and a compound is the combustion reaction, because the combustion reaction is always going to be an element plus a compound, but it's going to be a specific element. You're going to have a hydrocarbon plus oxygen. So you need to recognize the type of reaction based solely on looking at the product or the reactants, because we don't know what the products are. So let's try a couple of these. Let's identify the type of reaction by the reactants. So if I have lithium hydroxide and hydrochloric acid, lithium hydroxide is a compound. Hydrochloric acid is a compound. So I have a compound plus a compound, which makes this a double replacement reaction, compound plus compound. All right, so let's identify another one. Methane, or CH4, plus oxygen. Well, notice I gave you the name and the symbol, and CH4, that is a hydrocarbon plus oxygen. A hydrocarbon plus oxygen is going to give you a combustion reaction every time. All right, so if I have aluminum phosphide, notice no plus signs here, it's just aluminum phosphide. That is a single compound, which means this is a decomposition reaction, decomposition. And then we have copper plus silver nitrate. Well, copper is an element, silver nitrate is a compound. So I have an element and a compound reacting together, and so that's going to be a single replacement. Element plus compound, single replacement. Then I identify the type of reaction by the reactants. Again, we have calcium and sulfur, element plus element. This has to be a synthesis reaction. So we've identified the types of reactions based off of the reactants. And now we're going to go into predicting the products. So to predict the products of a synthesis reaction is actually fairly easy. We're simply going to combine the two elements into a compound, making sure to account for the differences in charges. So an example, if I have strontium combines with phosphorus. Strontium is a element, strontium, and it's going to combine with phosphorus. So if they're going to combine together, I need to figure out what the product is going to be. Well, the product is going to be strontium is in column 2, so it's a +2. Phosphorus is in column 15, so it's a -3. So when I combine them together, I have to account for that, and I have to cross the charges just like we did when we did the nomenclature. And so the 3 comes down here, the 2 comes down here, and I end up with SR3P2. So that is the product, strontium phosphide. So my strontium and my phosphorus combine, and I have to account for the charges whenever I create that thing. So my equation would be strontium plus phosphorus, which phosphorus is that special one, and so it's going to form strontium phosphide. That's a 2. And then I would need to balance my equation. I'm not going to do that right now, but I would need to balance my equation once I've predicted the product. So the product is going to be strontium phosphide. So if you think about it, I have strontium plus phosphorus makes strontium phosphide. And if you think about the words, then sometimes writing down the formulas is a little bit easier. To do a decomposition reaction then, we're simply going to take the two elements in the compound and separate them. All right, so we have a decomposition reaction is going to be a single compound. It's separated into its elements, and that's pretty simple. So let's look at the example of that. If I say water decomposes, well, what's that going to look like? Well, water has the formula of H2O, and if it's going to decompose, H2O is going to break apart into its hydrogen and oxygen. But what you have to recognize, though, is that hydrogen and oxygen are both diatomic molecule or diatomic elements. So that means they have to have their two when they're in their element form. So H2O is going to break apart or decompose into hydrogen and oxygen, and then I would need to balance the equation to be done. But these are my products. So synthesis reactions and decomposition reactions are really not that complicated. Single replacement reactions, on the other hand, are some of the more complicated ones because we have to account for that activity series. So the first you need to identify which element in the compound is going to be replaced by the lone element. So if the lone element is a metal, then it's going to be replacing the cation in the compound. If the lone element is a nonmetal, then it's going to be replacing the anion. So you have to pay attention. Is my element a metal and therefore going to replace the cation, or is my element a nonmetal and therefore going to replace the anion? That's the first thing you need to look at. The second thing you need to look at is check the activity series to see if the reaction is even possible. Can that lone element replace the thing it's trying to replace? If it can, then it does. If it can't, then it doesn't, and the reaction doesn't happen. Third, you need to make the new compound accounting for the charges. So let's look at the first example here. We're going to have lithium reacts with iron 3 chloride. All right, so we're going to have lithium is going to react with iron 3 chloride. So lithium is a metal. So it's going to try and replace the metal. It's going to try and replace iron. So the first thing I need to do is look at my activity series. Now, on the reference sheet I gave you, our activity series is over here. The most active stuff is at the top. The least active stuff is at the bottom. So lithium is trying to replace iron. And now lithium is at the top of the activity series, which means lithium can replace everything. So it can replace anything that's below it. So lithium can replace iron, so it will. So that means I'm going to simply have them switch places. Iron is going to be a lone element now, and it's going to be replaced by lithium. Now lithium is +1 and chlorine is -1, so their charges cancel out, and so they have no subscripts. So that is the correct way of doing this. So lithium is going to replace the iron, leaving iron by itself, and lithium and chlorine are now combined. And then I would have to balance this reaction. Okay, so that is the simple version. Now let's look at example number 2. In example number 2, gold reacts with copper to sulfate. All right, so we're going to have gold is going to react with copper to sulfate to produce something. So I'm going to need to look at my activity series again. So gold is down here and copper is up here. So gold is going to try and replace copper, but gold is below copper, and gold can only replace stuff that's below it. Well, on this activity series, gold is the lowest one. So gold can't replace any of these, okay? So gold cannot replace copper, so no reaction occurs because gold cannot. If I put gold and copper sulfate together, nothing's going to happen because gold can't replace the copper. So I want you to notice on the activity series, though, that hydrogen is right around here. So most of these things can replace hydrogen when hydrogen is in water or in certain compounds. Now there's ones that can replace hydrogen in water are these guys up here at the top, and we'll deal with that when it comes up. Okay, so that is our single replacement. You have to make sure that you pay attention and look at the activity series of whether or not it actually can replace. Let's do another example of a single replacement where we have fluorine reacts with calcium chloride. So in this case, we have fluorine, and fluorine is going to react with calcium chloride. Now, fluorine is one of our Brinkelhoff elements, so it's going to have a 2. It's one of the diatomics. So fluorine is going to react with calcium chloride to produce something. Now, what we have to do is look at this. Fluorine is a nonmetal, so this time fluorine is going to try and replace the anion. Because fluorine is a nonmetal, it's going to try and replace the nonmetal. Now, the activity series for the nonmetals, and the only ones we're ever going to deal with on this, are going to be the halogens. And the activity series for the halogens is the periodic table. The highest activity is at the top, the lowest activity is at the bottom. So fluorine is at the top. So fluorine can replace chlorine, bromine, iodine. It can replace any of them. So fluorine can replace chlorine, so it will. And our product is then going to be chlorine plus calcium fluoride. All right. Now, this is a 2 here because calcium is a +2 and fluorine is a -1, and I crossed the charges. It is not a 2 because it was a 2 over here. The 2 over here is simply because it's a diatomic. Now, chlorine is also one of the diatomics, so it needs to have the 2 also so that it would balance correctly. Okay? So whether your lone element is a metal or a nonmetal matters. Okay? So let's do another example of a single replacement. And this time I'm going to do francium bromide is going to react with iodine. Okay? So we have francium bromide +1 -1, so they cancel out. Francium bromide is going to react with iodine, which iodine is a 2 because it's one of those 7 Brinkelhoff elements, diatomics. All right, and so I need to look at the periodic table. Iodine is nonmetal, so it's going to try and replace the bromine, the other nonmetal. They replace each other. But iodine is below bromine, so iodine cannot replace what's below it. So that means no reaction occurs because iodine can't replace bromine, so there is no reaction here. Nothing happens. If I put francium bromide together with iodine, nothing's going to happen. So there you go. Looking at the activity series makes a difference as to whether or not the reaction actually occurs. Now, to predict the products of a double replacement reaction, you have to look at the solubility chart. All right, we switch the cations to form of each compound to form a new compound, making sure to account for the charges of the cations and anions. So you still have to account for the charges. You can't just switch them and keep the same subscripts. You have to switch them and keep the charges intact. Then you check the solubility rules to see if the reactions actually occurs. Okay, so let's look at our first example here. Sodium sulfate reacts with lithium chloride. Okay, so I have sodium sulfate is going to react with lithium chloride. So what I'm going to do is I'm going to switch the partners. So what I'm going to do is I'm going to take my anions and just switch them. So that's going to give me sodium chloride. So the sodium is now combined with chlorine. Sodium is a +1, chlorine is -1, so it stays NaCl. And now my lithium is combined with sulfate, Now lithium is a +1 and sulfate is a -2, so when I cross the charges it's Li2SO4. We have to keep the charges intact. All right, so now the question is does this reaction actually occur? So I'm going to look at my solubility chart. Now the way this works is all of these things are soluble unless it's one of these exceptions. So for example, sulfate, SO4, sulfate compounds are soluble unless it's strontium, barium, lead, or mercury. Well, sulfate combined with sodium. Sulfate combined with sodium, that's not one of the exceptions, so sodium is soluble, okay? Because it's soluble except when it's with these. Chlorine, all right? Chlorine is soluble except when it's combined with those. Well, lithium's not one of those, so that is soluble. Again, chlorine is soluble except when it's combined with one of these three, and so that is a soluble thing. Sulfate, again, is soluble except when it's with these four compounds. Lithium is not one of those. So all four of these are soluble. And since all four of them are soluble, nothing really happens. They stay as their ions. So we're going to say that this is no reaction because all four of those are soluble compounds. So when they're all soluble, we say that it is no reaction takes place because the net ionic situation, these are going to break apart into their ions when they're in solutions. We talked about that in a previous video. They're going to dissociate into their ions. Well, the ions don't really change anything, so we're going to say that that reaction doesn't actually happen. Example the second. Lead nitrate mixed with potassium iodide. So now we're going to have lead nitrate mixed with potassium iodide. So if I have lead 2 nitrate mixed with potassium nitride, well, this time I'm going to switch my positive ones. It doesn't really matter which ones you switch. It just, makes life a little easier. Okay, so lead nitrate, potassium iodide. So this time I'm going to have lead iodide, lead 2 iodide plus potassium nitrate. Now I'm not worrying about balancing these right now. So I've written them out. So instead of lead nitrate, I have lead iodide. Instead of potassium iodide, I have potassium nitrate. So they switched partners, switched names. So now we need to look to see if they are actually soluble. So we look on here and we see that nitrate compounds, NO3, nitrate compounds are soluble with no exceptions. So that means lead nitrate is soluble. And iodine is soluble with these exceptions, silver, lead, or mercury. Well, potassium is not silver, lead, or mercury, so that is soluble. So both of these are soluble. And then we have lead iodide. All right, iodine, again, is soluble except when it's combined with silver, lead, or mercury. Well, that's lead. So this is one of the exceptions. So this is not soluble or insoluble. All right, and now nitrate is soluble with no exceptions. So soluble, 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 not soluble. So that means this is the precipitate. It is the insoluble solid produced. So this reaction does occur, and these are the products. So we look at the activity series on single replacement. We look at the solubility rules for double replacement reactions to determine whether the reaction actually happens and then to predict the products. Now we're predicting the products of a hydrocarbon combustion reaction. You should never get these wrong ever because they're always going to be the same. Products are always carbon dioxide and water. Once you have identified it as a combustion reaction, the products are carbon dioxide and water, always. CO2 plus H2O, always. All right? So, butanol, which is C4H10O. So, C4H10O Butanol reacts with oxygen. That right there gives it away that it's a hydrocarbon plus oxygen is going to make a combustion reaction. So the products are CO2 and H2O. Every single time, I don't have to put any thought into it. Once I've identified it as a hydrocarbon combustion, the products are CO2 and H2O every single time. Couple of things that you need to think about. It's usually easier to make predictions by thinking of what the chemical name would be and writing that formula name. So when we were looking at the double replacement, we had lead nitrate combining with potassium iodide. So lead nitrate, potassium iodide, switching the names was going to give us lead iodide and potassium nitrate. So switching the names, thinking about it in terms of the names first, and then writing the formulas using those IUPAC rules, you're usually going to be better off getting the correct formula if you do it that way, rather than trying to look at the formulas. If you just look at the formulas, then oftentimes you're just going to write the same symbols that you wrote before, and the subscripts would all be wrong, and then you wouldn't be able to balance the equation. So look at the names of the compounds and try and predict the products thinking about what the name would be, and then write the formula from that. And you make sure that the formulas are correct so that the equation can be balanced. If you do not have the correct formulas, then sometimes it's impossible to balance the equation. So if you're trying to balance the chemical equation and it's not working, and no matter what you do, you can't seem to get it to balance correctly, you need to ask yourself, did I write the formulas correctly? Because if the formulas are wrong, then you cannot balance the equation most of the time. Right, so predicting the products is a really important skill. It's very much what chemistry is. So knowing what you're going to get when you mix two things together is a very helpful skill. Knowing why you shouldn't mix this compound with this compound. Well, because when I mix this with this, it's going to make something else, and that something else may not be something I want to be around. Keeping that in mind, that's why we go through how to predict the products. With most of them, it's fairly simple. The single replacement and the double replacement reactions can be a little bit more complicated, but I think you'll get it with some practice as you go through and do a little bit more practice of looking at that activity series, looking at the solubility rules, and just learning how that all works out. So thanks for watching. Have a day.